PhD candidate in transportation engineering at Technion. He completed his master's degree with honors in 2019 and his doctoral degree in 2017. Also at Technion, he presented his PhD and master works at several international and local conferences. As a transportational scholar, Yazan's motto is transit and control the traffic as the air, transport, blood, and oxygen. And the subject of presentation is modeling and control of low-altitude air city transport systems.
Thank you, Mark. Moment. Hello, everyone. I'm very excited to be here today. So my name is Yazan, and I have a nightmare. One day, the sky will be congested as our urban street. Recently, air transportation system is rapidly changing, and with the increasing number of passenger delivery aircraft in the urban airspace, in the low-altitude airspace, it will cause congestion and control challenges. We believe that traffic management and control for the urban airspace are needed. In our work, we have a few main challenges, and we are focusing in modeling and control. So first, we need to model the aircraft dynamics and behavior in the airspace, and then we want to capture also the macroscopic level, the whole airspace dynamics. Then, based on that, we can develop aircraft controller and command system in order to operate the system, and also develop traffic control strategies that we have in the ground systems. All of this needs to be simulated, also the model and the control strategies, and to verify the optimal solution. In one sentence, the whole project idea is to develop traffic flow and feed the control theories for low-altitude air city transport and short-flat systems. And today we are presenting a recent work that we are doing. We just submitted it to ISTRC, where we develop a departure and a boundary control. What does it mean? It means that if we have the urban airspace, we have a control tower that operates in a specific radius, then we can define our network, which we believe we should divide into layers and regions. Each region has its own traffic characteristics, and according to traffic flow models, we can know if it's in congestion or free flow condition. One of the first things we did is that we said, okay, if it's congestion, we don't allow any more departing within this region. But they don't travel alone. There is more regions in the airspace. We have traveling aircraft within the layer, so we should also take this into account. And the traffic flow models is affecting each other, the characteristics and the dynamics. So again, we can develop a departure controller to control how many aircraft depart from within each region. But we can also control the boundaries to stop them before crossing the main area. So this is the definition of the problem of departure and boundary control. How we solve it? We solve it with a unique operational framework, where first, as I said before, we model the aircraft dynamics and routes. This is for a single aircraft, but we have more than one. So we have, for each aircraft, we have a kinematic model where we capture the velocity, and we add states called future position. We can go into more details on this topic in the Q&A. Of course, it's have a maximum velocity and it's around, but we have more than one. We have multiple aircraft in the sky, and we need aircraft controller to maintain a collision-free flight. So we solve that with the artificial potential field approach, where for each aircraft there is two tasks. One, to fly into the waypoint, to the destination, and second, to maintain there is no collision. For this, we form more states in the system and look at the derivatives and the errors between them. We have two functions for each task, and at the end, we get the velocity command. Then, we can have a full operation of aircraft in the system, but this is only in the microscopic level. We want also to look on the macroscopic level. So we aggregate the aircraft trajectories, and we formulate the MFD concept, the macroscopic fundamental diagram concept, where we know the accumulation, the number of aircraft in the system, according to the output, to the throughput of the system. Then we can know if we are in free flow on the left or in congestion on the right. This we do with end determination, where we look at the time spent and the distance of each aircraft. We aggregate the information information, and then we can formulate this, the average speed, density, flow, and outflow in the system. This gives us identification, what is the condition in the airspace. And we can do that simultaneously in the same plant, in the same framework. And we capture the micro and the macro levels of that operation. How it looks like something like this. So we have, on the left, we have the plant, the aircraft dynamics, and the trajectories, and on the right, we have the macroscopic fundamental diagram concept. But before going more into the 3D option, we want to focus on the 2D option and to prove it until the end. So we are now investigating the 2D option, and we notice that it's not the whole airspace that is congested. Some regions are, and some regions are not. So we need to develop a model for that. So we propose a control model based on the MFT concept, where we basically, according to the conservation law, the input minus the output in each region, the accumulation, the derivative of that, how much it changed. Then we can control the input by changing the departure time. Or we can change the output by changing the outflow and make them stop on the boundary. This is just a simple model, but actually we need a more complex model for that, where we look into the one that are the traveling aircraft and the queue dynamics as well. Because we cannot store them in the airport or in the boundary as much as we want. There is capacity for that. So this is the more states in the system. So based on the control model and dynamics, we can formulate a feedback control problem and to optimize the airspace state. We use the MPC approach. Basically, this is the optimal control problem. We have an objective where we minimize according to the control inputs, the dynamic, constraints, and initial values. I wish I could write it down in the slides, but it's just no space for all the equations. We solved it with MPC. MPC method, model predictive control, is basically looking or predicting the future according to the dynamics, and according to that, to optimize the control inputs in the system for the macroscopic level. Then we want to go back to the microscopic level. So we need the aircraft command block, where we take the optimal control inputs for the macroscopic level, and we convert them to the microscopic, to the aircraft level. So there's an algorithm for the departure controller and the boundary controller. I'll not go into details, but basically we transform the optimal solution for the whole network to the aircraft, to the agent in the system. Then we are back. We manipulate the departure time of the aircraft, the velocity command, and the path of the aircraft. All of this is in the same framework, where we have the microscopic and macroscopic level of flat operation, both in modeling and control. This is how it looks. On the left, we have only departure controllers, so we only stop them from departing from the ground. In the middle, you see them stopping on the boundary, in the middle. And on the right, we integrated both approaches together. Of course, the beauty is that when you integrate both approaches, we do a balance in the system between the supply and the demand. This is how it looks like. This is the plant results. Of course, we look also on the macroscopic level, on matter of total time spent in the system, and with integrating both approaches, we make a better performance in the system under different demand profile. This is how the MFT looks like from undersaturated condition to oversaturated condition. The departure controller is a bit limited when demand is too high, because there is storage capacity in the vertiport, in the ground. Just to conclude, the MFT model help us to model, detect, and avoid congestion in the airspace. And in this unique framework where we both capture the micro and the macroscopic level of flat operation, both in modeling and control, we can develop control strategies in order to make a better operation. We have future direction also to include some of the energy concept in this approach, and to calculate what is the energy consumption of each aircraft. This looks like something like this, where we look also on the battery, how much it is, and to see the aggregated value for the whole airspace. So far, you can read more about this research in this publication, and I would like to thank the sponsors, ISTRC, for this, and the European Alliance,